Okay, hello everyone. Thank you for joining for the session today. Today we have a talk on the math behind AI generated images. Uh, it's like very interesting talk to me. Our speaker for today is Atif Ali, who is my friend and colleague here at University of Liverpool. He's a data scientist and work at the Faculty of Health and Life Sciences. Yeah, so thank you very much, Atif, for agreeing to give this talk, and I look forward to it.
Hi everyone, so thank you for joining in today, and I hope you learn something very valuable from today's session. So topic is the math behind AI generated images. Outlines are this. So first I will introduce you to generative adversarial networks. What are neural networks? And then how neural networks are trained, then GANs training and GANs formulation, and then last references. So nowadays AI can do a lot of stuff like we can do music generation, audio generation, video, images generation, and text like ChatGPT. So AI under the hood, it doesn't see anything, but it only calculates numbers. All it needs is probability, vectors, and optimization. So here's a quick demo. So this website, this person does not exist. If I click on this, um, can you see this picture?
I think you have only shared the PPT, so we cannot see the link.
Can you see it now?
Still no.
Just,
I think you have only shared. Oh, okay, we can see it now.
okay, so this person does not exist. This lady is not real, and it's actually a model's output GANs, the today's topic which we are learning about. It can be seen style GAN 2. Every time I refresh this page, it will show me a new image. And these pictures look so realistic, but it's generated by AI GANs. So every time I refresh it, it will show me. So you can give it a try and see the output. Share to. Can you see my slides now? Okay. Okay. So GANs were the time. These are how GANs get more and more advanced. So they were first developed in 2014, and this is how its initially performance looked like. And then with the passage of time in 2018, it got much better, and this is how the images are created now. And so these are the GANs model were introduced by Goodfellow and the researcher from University of Montreal in 2014. It is a neural network that belongs to a set of generative AI, and they can generate new content that has never been generated before. So as I said, that generative models can be applied to various domains such as images, music, speech, and writing. So in GANs particular, it works on two neural networks, generator and discriminator. So first, I want to explain what are neural networks. Some of you might have heard of it, but I would just give you a quick recap. Neural networks are
Atif, Atif, sorry to interrupt, but there is a bit of noise coming, so I don't know if it's my network or it's just I don't know.
Can the audience confirm it if it's
I think it's better now. Maybe I don't know you are a
okay?
little away from the mic or it was not an outside noise. It was from the computer system, I think.
Okay. Is it working properly now? Or-
Um, it's better. Yeah, it's better now. Yeah, I think I think you might have issue in the mic. So yeah. Okay, please continue. Please continue.
Okay. So neural networks are inspired by how human brain works. They consist of multiple layers of interconnected neurons that pass information. So this is how a brain's neuron looks like, and there are billions of neurons in our brains that send information to each other. The way we understand the universe and see everything here and everything and comprehend them is because of these neurons working together and make sense out of the everything we see are here. So this is just a single neuron in our brain, and it will be connected to other neuron this way, and all. And then this is how. So the inspiration was from the artificial neurons. These were inspired by how the human neurons were. So in artificial neuron structure networks, it follows kind of similar structure. So multiple neurons here. This in here, it's just a single layer, but there could be like hundreds or thousands of layers, and within one layer, there will be numerous neurons. This how it works, the artificial neuron. So it takes an input values, then it calculates some numbers, multiply it, transform it, and it gives us output. This is a single neuron zoomed in. So let's say this one. Um, so these are the inputs, could be any numbers we are working. Then bias will be added, and then weights, it will be multiplied with weights. And then linear, you might have heard of, like you have worked with linear models, which are very simple, y is equal to mx plus c. So neural networks are actually, they're following the idea of linear models, but it adds one other thing, which is activation function. So it adds the non-linearity to the linear models. So here it goes, and it's very simple. So it will just, so there are examples of activation functions, sigmoid relo, and it will, some of them are very simple. So it will either uh, take the maximum value between zero or the actual value. So it doesn't do any advanced mathematics or anything. So, and with enough neurons in neural networks, it can model any mathematical function. That's why these are so used in the industries, and that's why it's so important nowadays.
Atif,
Yes.
uh, um, can you try again to check your audio setting? Maybe I think just check which audio you have shared. Um, See if it can be improved a little. So just check maybe if you have, I don't know, microphone and the first option in that one, and maybe, uh, yeah, I think the speaker one is might be fine for you.
Um, Just give me a minute.
It's your mic issue. It's not from the outside.
Uh, Let me check if I got another mic. Much.
Okay, let's
Okay.
go ahead.
Okay. So my slides visible?
Y-
Yes,
y-
no.
Yes, yes, yes.
Okay, okay, okay.
Yeah, your
So,
video is turned up, but your slides are
okay.
visible.
Uh, so yeah, so this is how neural networks models are trained. So we have input layer, which are numbers, the data we are working with. Yeah, so it's also called feature vector, and then we do some linear transformation. So we multiply all the inputs with weights, and then add bias with it, and then ReLU function. As I explained, there it could be ReLU, sigmoid, and the output of activation function is actually the output of the layer or that neuron, and then we determine the loss for continuous numbers. For regression models, uh, it could we use mean squared error, which is predicted value minus actual value, uh, power 2, and then divided by 2, and then it determines the loss value. If the loss, then each using chain rule to compute gradients. So it uses back propagation method, and we take the partial derivative of loss function with respect to all W weights in the model, and then we update the weights, the parameters, using this formula. So we have learning rate, which could be it's a constant, and mostly it's taken at 0.01, which is very small number. So mostly it's taken as then all the parameters are updated, and next time this loss will be lower than the previous one, and then the goal is to minimize loss, the mean squared error. So this is how the neural networks are trained. In generative networks, since we are working with two models, discriminative models and generative models. So the way discriminative models work, they are just simple classifiers. So we give it input of some features, and it tell us about which the class these features belong to. So if we train a model on images of dogs and cats, and then we give it image of a cat, it will tell us that this features belong to cats class. So it tells us probability of class given the features. So discriminant,
Atif,
yes.
I'm sorry, I have a little bit of issue in the screen. So can you unshare and share again? Uh,
Okay.
I guess.
Mm, I hope it's visible
Yeah.
now. Was it only to you or everyone?
I don't know. Maybe it was just me, but no, it's
Could
okay.
okay. So
Yeah.
yeah. Discriminative models work as classifier. It classifies features, learns to distinguish. So in GANs, the only work it does is it distinguish between real and fake data. Real data is real world data, and fake data is the one which is generated by generative models and GANs. So the way generative models work, it takes some noise and then takes a class, let's say a dog class. It would just take a label. So noise plus dog gives us features of a dog. So image, let's say, for example. and probability of features given a class. So this is how generative model. It create features given a class, and this one give us class given features, so opposite of each other. So generative models learn joint probability distribution of real data and generates new data from random noise. So the main idea behind GANs network is that we have one, as I mentioned, generator and discriminator. Generator creates fake data, fake images from some random noise, and then it's sent to the discriminator. Discriminator has access to the fake image generated by generator as well as the original data. So it knows which one is fake and real. And all it does is to give this image a label of fake. This one acts as a detective. So it will say that the image you created is fake. And all generator wants is to get better and better so that it can fool discriminator to uh, it cannot identify if the image generated by generator is fake or real. So as I said, generator creates fake images from random noise. Here is the random noise. It could be uniformly distributed noise or Gaussian distributed, and then the discriminator attempts to distinguish between real, this one is real, and fake images, fake from here. So the generator improves by trying to fool the discriminator into thinking the fake images are real, as I said. And training is complete when discriminator can no longer reliably tell if an image is real or generated. At this point, the GAN is considered well trained. So this is how. So in first attempt, so let's say if this is a real image and we want the GAN model to be able to generate images like this black cat. So generator doesn't know anything about this image, and discriminator has got access to this image. So what generator, all we need to in training the GANs model. So generator is able to generate fake image like this so that it looks real. So the first attempt generator does is that it just creates a very random line or anything because it doesn't know anything about it just takes samples from the noise distribution and creates a random line, and it's very easy for discriminator at this point to identify that this image is fake because there is a big difference between this and this. After some attempts, generator learns that I should not pick those data points from that distribution. It learns the joint distribution of real images. And after some time, it learns to create images which look a bit more realistic to the real images. But still, discriminator will say, no, it's fake. And even ultimately, generator learns the joint probability of the real images, and it can actually pick the actual distribution data from noise of real data, and it can generate fake images which look exactly like new images, and discriminator will no longer tell if this image is real or fake. So at this stage, the GAN model is considered to be well trained, and we can generate images from it. This is an architecture of the GANs model. So here we got real world data and sample from it provided to the discriminator, and then here we have some noise, and then it takes sample from this noise, which is a vector, then provided it to generator, uh, and then this is the sample from the noise, and then also provide this one to discriminator. So initially it can easily identify if this sample is fake, and because this one it will check it with the real, and it will say if this is real or fake, and then loss. This is the discriminator. It discriminator only outputs one value, which is probability that the image is real. So initially it will just output 0.1, 0.2 low probability, and with time it will get better as the generated images will be better. And so this is the probability of discriminator of real images. It will be always one, and then discriminate. This is the probability of discriminator for generated images, which is G of Z, generated images. So for the discriminator part in GANs, this is how it stands. So it takes features, which is samples. Let's say these samples could be these or these, and then neural networks. All the samples are multiplied with the parameters, and then it give us an output, which is probability that these features belong to real data. And if it shows wrong probability, the cost will be high, and it will be compared with labels. The cost would high, and again this is an iterative process, so again the parameters will be tweaked. So next time it will result better performance in terms of the determining if the image is real or fake. So with time, generator is getting better and better, but discriminator is also getting better and better in identifying the images, classifying the images, either it's real or fake. So yeah, these are the image features. It gets into these neural network, and gives us output that this image is 0.05. Probability of this image to be real is 0.05. So all discriminator is doing here is that probability of real class given these features. If this was an actual image, the value would be quite high, but this is a fake one, that's why its value is low. So GAN's objective is to make generated and real distributions look alike. Let's say this is the real world distribution data or real images data, and these are the generated image data. So initially these two will be very far from each other, but the model gets better and better. These will come closer, and generated data will look exactly like the real data. So generated data probability distribution will be similar to, in ideal situation, the actual data here. GANs formulation. So this is the objective function of GANs. So this is how it works. It's formulated as a min-max game where the discriminator is trying to maximize its reward. This is the reward function for discriminator, not generator. So discriminator wants this value to be high and high, but the generator is trying to minimize discriminator's reward or maximize its loss. So this formula contains two parts. This one is for the real image, this one is for the generated image. And here, if we ignore log, the d of x is the probability of x is real data and d is the discriminator model. So it gives us one value, which is probability of real image. And then in here, z is the random noise, G is the generator. So this means the features generated by generator. And if we give it to discriminator, it will give us a probability that this features, this Z belong to real class. So initially it would be very low. These are for the fake images, because discriminator can easily distinguish between real and fake data. So initially it would be very low, this one would be high. So all generator wants is to minimize this part of the equation so that the discriminator can tell that these are actual images, real images. So generator's goal is to fool the discriminator or maximize the log of G. So these are for the output of discriminator for the fake data. So it wants this value to be high, or practically, if we see it's 1 minus D, so it wants this value to be minimized, or this value to be maximized and this value to be minimized. And discriminator goal is to correctly classify real versus fake images. So maximize this entire term. So maximize this one for probability of that these images belong to real class, and then for fake, so it will give us low value and 1 minus high value. So it will discriminator will try to maximize this entire function. So the way in training process, it's alternating optimization. So first step is to fix generator and update D to maximize the objective function. So in this way, both generator and discriminator are trained. And then in the second step, fix discriminator, update G to minimize the object function. And at equilibrium stage, ideal would be to when the probability distribution of generated data is equal to probability distribution of the real data. At this stage, discriminator can no longer tell that if the image is real or fake for all the images, for all the, so it will always give us value of 0.5, that it will be confused either this image is real or fake. This is how the discriminator laws look like. So initially, it's very high for the yellow line shows fake images and fake data. The blue one, real data. So for the blue one, it shows high because the GAN model is not trained. It will show high value for real data and low value for fake data. But as the generator gets better and better, it will with the passage of time will try to fool discriminator, and it will show high and high value for the fake data, and ultimately it will be converged to somewhere around 0.5. And at this stage, this GANs model can create new images very clearly. And these are some of the references. And yeah, that's all from my side. Thank you for listening. Any questions or?
Thank you very much, Atif. It was very interesting talk. Yeah, we can go ahead and see if somebody has questions. Um, yeah, we will share the slides. So in those of you who's asking for the slides, so maybe Atif would try to make it more complete or put any details that you may need, and then we will share it. So